Hi. Today we're going to talk about Newton's laws of motion. And most of you have heard the story about Newton sitting under an apple tree and an apple fell on his head and he came up with the whole idea of gravity. Well, that event probably didn't happen. But what did happen is that during his university years, there was an outbreak of bubonic plague in London and the surrounding communities. And he left the city and went to his family's estate and stayed there for 2 years and had an awful lot of time to contemplate things. And it is said that it was there that he first started to develop the whole idea of calculus, and he spent a great deal of time thinking about light and prisms and so on. So here's Newton in all his glory, and when he first came up with the idea of inertia, which is his first law, he put it something like this. Every body continues in its state of rest or of uniform motion in a right line unless it is compelled to change that state by forces impressed upon it. Okay, but let's think about that in terms of modern English. So here we have an example. The driver of the motorcycle and the motorcycle, we are assuming, were speeding around a track. So they were moving as one unit. They then came in contact with this wall of tires. The wall of tires is exerting a force on the motorcycle, but it is not exerting a force on the person, so the person riding the motorcycle continues along at that same speed. So there was a force exerted on the bike which stopped it, no force exerted on the driver continues on. So, here's how we're going to put it. An object will continue in a constant direction with a constant velocity until an unbalanced force acts on it. In other words, something is going to continue to do what it's doing until an unbalanced force changes it, whether it speeds it up, slows it down, or changes its direction. So, inertia basically is a measure of an object's resistance to a change in its motion. How much is this object resisting speeding up, slowing down, or changing direction? And it's sort of logical, you know this, that the mass of the object is going to determine how easy it is to change its direction. Something that's really, really heavy is not going to be as easy to move, to start up, to increase its velocity, or to slow down or to stop. So the greater the mass, the greater the inertia. And here's a great example. The truck put on the brakes. The truck is traveling at a certain speed. The friction on the brakes is what slows down and ultimately stops the truck. Well, the brakes do not act on the stone. So we're going to assume that he slammed on the brakes, the truck came to a stop, the stone does not come to a stop because there's no force exerted against it. There would be a little friction on the floor of the shipping container, but the rock keeps going until it comes to a stop against the cab, and that's the force that gets it to stop. This one, we see a skateboarder on the ground, so we're going to assume that he was riding his skateboard, it came into contact with that crack in the road that had been filled, there's a change in the frictional force increases, it stops the skateboard, but the person riding the skateboard, it does not stop because it exerts no force on him, and he keeps going. I like this one. The brake pads on the front tire are exerting a force on the tire and therefore the wheel. So the front wheel comes to a stop. Well, you can see by the design of a bicycle, the front wheel stops. That doesn't mean the back wheel stops. So the back wheel continues to go. The person riding the bike also continues to move, and this does not look like it ends well. I don't know if it's someone trying to do a trick or impress the ladies, or I don't know, but anyway. This is one of my favorite pictures. The sumo wrestler there, huge amount of mass, huge amount of inertia, and this little boy who might be 5 or 6 maybe, is trying to move that gigantic mass with its gigantic inertia. and it cannot be done. All right, Newton's second law is actually an equation. Force is equal to mass times acceleration. So, as we look at the formula, we can say that the acceleration of an object, remember acceleration is a change in velocity, speeding up, slowing down, changing direction. The acceleration of an object is directly proportional to the net force acting on it. Directly proportional means they're moving in the same direction. So as the force exerted on an object increases, the object is going to go faster. It's going to increase its acceleration rate. And that makes sense. You know this. If you sort of toss a ball, it's going to go at a fairly slow acceleration. If you whip that ball, you're just increasing the amount of force you exert on it, and it's going to go really fast. However, the acceleration is inversely proportional to the mass of the object. For example, if you had one of the ball bearings we used in class and a ping pong ball, and you flicked them both with your finger, the ping pong ball is going to take off at a huge acceleration rate, whereas the ball bearing, not quite so much, because of its enormous mass. The last part of this F equals ma formula is that the direction of the force and the acceleration of the object are in the same direction. So when you flicked that ping pong ball, your flick is the force, and the direction your finger moved in, which we'll call forward, is the same direction that the ball moves in as it moves away from your finger. So the direction of the force and the motion are in the same direction. So I love this picture. So here we have a little puppy who's probably a few months old, learning how to pull a sled. Little puppy, not a lot of force, not a lot of muscle, pulling on a sled. The sled is fairly light. The man is not on the sled. Not only that, look at the surface they're moving across. Snow, little friction. So there's not a whole lot of force acting against the movement of this either. So there's not a lot of force, there's not a lot of mass, there's not going to be a great deal of acceleration here. However, if we look at this picture, now initially you can see two dogs. If you look really closely, you can notice that in fact there are actually 4 dogs there. So we have 4 full-grown dogs, a lot of force. The mass of the sled is greater than it was before because now the person is standing on it. And the acceleration is much greater because of the greater force, because you have 4 full-grown dogs instead of just one tiny puppy. Now this one, the force exerted on the man, or not the man, but the force exerted on the car is equal to the force exerted on the bug. And you'll say, wait a minute, that can't be true because the bug is splattered and the car is not. True, but let's think about the change in velocity. When the car hit the bug, was there a detectable change in velocity? No, but the car's mass is huge. So we have this huge mass, a tiny, tiny little acceleration or change in velocity, right? Then the bug, however, the bug was moving, oh, I don't know, let's say a couple miles an hour in a forward direction, and then the car comes along at 30 miles an hour. So the bug not only changes from a positive direction to a negative direction, but also changes from moving at 2 miles an hour to moving 30 miles an hour. Huge change in velocity, huge acceleration, change in direction. Tiny, tiny, tiny little mass. The force that the bug exerts on the car is the same as the amount of force the car exerts on the bug. We'll talk about this more. Here's another good example. We have a golfer swinging a golf club against a golf ball and then swinging a golf club against a truck. The force that the person swings with is exactly the same. Because the mass of the golf ball is really tiny, the acceleration is going to be enormous. With the same amount of force exerted against a truck, the acceleration is going to be infinitesimal because of the mass of the truck is so enormous. So mathematically, the forces come out to be the same. It's just they have a greater mass and a lower acceleration, or a low acceleration and a greater mass. The third law has to do with action-reaction pairs. You may know this law as for every action there's an equal and opposite reaction, but we're going to reword it because that implies something that's not actually true, and it uses the terms in such a way that we think something that's not actually true. So let's look at it this way. Whenever objects interact, there are action-reaction force pairs that are equal in size and opposite in direction. Okay? So we're going to call this action-reaction pairs. The action-reaction pairs are equal in size and opposite in direction. So if you look at that little drawing over to the right, we have 3 people and a rope. There's an action-reaction pair between the stick figure on the right and the rope. There's an action-reaction pair between the stick figure on the left and the rope. And there's actually also an action-reaction pair in a vertical direction instead between the stick figure in the middle and the rope, because she looks like she's pushing down on it. Now if we looked at this further, we could also find action-reaction pairs between all of their feet and the floor. So there are 6 pair of feet, so there would be 6 pair of action-reaction forces. This is one of my favorite pictures in all the world, and we can look at action-reaction pairs here as well. There's action-reaction pairs between the glove and the blue book, and the blue book and the red book, and the red book and the green book, and the hat and the cake, and the fish and the rake, and the boat and the finger, and the toes and the plate. They're everywhere. They're equal but opposite. Now, let's look at this. Action-reaction pairs. The force exerted from the foot onto the nose is exactly the same magnitude, but opposite in direction, of the force of the nose, of the force that the nose is exerting on the foot. All right, but who's in more pain? Well, the guy in the white shirt, because of the lower mass of the foot, the lower mass of the nose, there's a greater change in acceleration of the nose, and therefore there's more pain. And the foot doesn't feel much at all. This one's kind of gruesome. If you don't want to listen, if you don't want to look at this, just look away. But I chose this picture because what it shows is the results of an action-reaction force with a seat belt. Many of you know the seat belt is what prevents you from flying through the windshield when there's a crash or the brakes are slammed on really fast. So the seat belt is exerting a force against the man. The man, in turn, is exerting the exact force but in the opposite direction along the seat belt. Okay, so here we have a rescue dog. The rescue dog is jumping off a boat. In order to do that, he needs to push against the boat. That push against the boat, what's actually happening is the boat is pushing on him with exactly the same force that he is pushing on the boat, which allows him to jump out into the water. Now, the dog has a significantly lower mass than the boat, so when the dog jumps, we see a great acceleration with the dog, but we see very little change in velocity or direction with the boat. So the forces are the same, they're opposite and equal, but because the masses are different, the accelerations are going to be different. In this particular case, let's assume that the dogs have the same mass. They look about the same size. If this dog jumped off the kayak, what would the results be? The dog is still exerting a force on the kayak is exerting an equal but opposite force on the dog, and the dog will jump off the kayak. But unlike the bigger boat in the previous picture, this kayak weighs significantly less and is actually going to react by accelerating in the opposite direction. The boat still weighs more than the dog, so it's probably not going to accelerate as much as the dog, but it's a closer mass than it was in the previous picture. So we've made our way through Newton's laws. If you have any questions, feel free to bring them up in class. And otherwise, thank you for listening.